By now, with the module I've been working on with you, you reach a certain level of metallurgy that is more than what I've done other semesters, because we talked a little bit about grains, then we went all the way to dislocations, and I think you guys a little bit understood what happens when we do the forming, hot forming, and why we're doing it. So we will graduate from that, and one thing that I didn't complete on Tuesday was the discussion about some of similarities and differences with plastics, so we're going to do that today. And then the only really, bulk material topic that we haven't approached is heat treatment, so we're going to do that tomorrow. And then, of course, there's plenty of surface treatment and joining and cool things that you can do to improve the material properties, so that's what is going to follow next week and the following. So time goes on pretty quickly. There are a few people that came to me with their ideas of their term presentation. If you haven't done that yet, it's probably a good time to get your mind started. Like, you can just say, well, I'm thinking about this topic, and then we can easily expand and give you ideas on how to frame it in a way that, it's interesting to you and also the class, because you have to present to all your colleagues. This is going to be good. Now it's not moving everywhere. I cannot understand why it's only when I come here that I have to restart my computer. It's not, I don't think it's the connection. One of the main topic, I know Professor Eager has been emphasizing with engineering, it's a very broad discipline, right? And you may be called to do all sorts of, all the way from administration to pretty advanced R&D, depending on your skills, your interests, and where you work. Maybe one way that I think of it, we have to differentiate ourselves, right, from other business people or other researchers. And I think one general aspect that we're trying to do is to design components that meet exactly the function, not more, not less. I think that's one of the uniqueness, and that's why Professor Eager is talking about factor of safety, because ultimately, one goal of engineering is to know what is a sufficient factor of safety. And a lot of that, we do learn it from failures, unfortunately. So that's one thing that we're going to go on today. I will teach you a little bit how we learn from a failure to essentially make a better design or a better product or a better process, depending on what the case may be. So we're kind of at that breaking point where we're going to start with plastic, go into a little bit more of the failure mechanism. See if this allows me to add everything ready. While it's still loading up, let's talk about a fracture surface, because from experience, I've learned that you don't necessarily all had the opportunity to pay a close attention to what we see here. So there are two main categories of lines on a fracture surface. One that I'll call the crack propagation lines, and I'll put a few here. This is an axle for a train. So this one is a crack propagation line. And then we have a lot of smaller crack arrest line that are also called beach lines. I'm going to draw these. You'll see a lot of them here. So this continues in both directions. The main difference here is there's a step where we have the crack propagation line. Then we have this, for reference, we have an initiation somewhere around here. We have another initiation here. And we have another initiation here. Three main initiation sites. And the final thing, this is the amount of metal, roughly, that was left on the entire cross section when it finally broke. So that's, the good thing is it's so big that even if I don't get exactly to you, you'll still see. So, like this. The reason I know that there was a big, the main initiation was somewhere here is there were a few cracks that were slightly at different heights, and they all essentially emerged just like sun rays from this area. Now, when I look at this one, this is essentially a step. There's no good relationship between this cracking and this cracking. It's when they came together. So that means there was another initiation somewhere here. And then the final line, if you see, are positions where the crack was at a certain point in time. So it's not straight. It's a very, very local position. So at a certain point, we had something like here with the step and then going all the way here. We have the same on the other side. So a lot.
And this is the region that...
That's the final failure, yep. So all the way to here, you're still in service, which is crazy. But it's very hard to inspect some of these components. So I've seen shafts of this size for elevators fail in the same way. And
where are the points of initiation?
So if you look over there, we have one around here. We have another one here, and we have another one there. Then the reason I say that is you see all these crack propagation lines, just like sun rays, that go from this location. And then you see the crack arrest lines over here. We call it beach lines. So at a certain point, the crack was kind of having this type of profile here. It's a very particular profile, if you will. Initiation, and then you have multiple regions coming from it. Then you have another initiation here, and then they merge. That's why there's a big step over here. And then the other side acted completely independent, and over here you have the final failure. And the good thing with this example is you can see at any point in time where the crack was, because you have these little lines that are very closely spaced, and we call those beach lines or crack arrest lines. So at a certain point, the crack was arrested at a given point. It doesn't mean, so the one that's a little more subtle, the crack arrest line, it doesn't mean you can count cycles, because it's very likely that it's when you have an overload. So each time you load the locomotive, you get one line, as opposed to getting it, each time you turn. Because otherwise you wouldn't have much service here. So it doesn't mean that the cycles are constant, but you see the lines emerging from this area. Then there's another one emerging from this area. There is a special surface treatment that we can see here. And there's another initiation here. So this was growing at the same time as this one. So the crack propagation line tells us the main propagation direction. Crack initiation with a bunch of different ways the crack was going. It's same over here, and then they eventually get together. And at the same time that this was happening, you had the same thing going on the other side. Those we see well, but those are the crack arrest line. The crack was pretty curvy at any point in time. When you get to here, then you just have reinitiation and cracks starting from here and going to the center again. So we know it's not here. This is definitely a main initiation site. Because this crack is bigger, I say that it's really started here first. But there were a lot of initiations. I think that's one aspect to keep in mind. And we can't essentially blame one inclusion as the cause of all this. Have you seen it? Mm-hmm. So we have essentially an initiation over here, and the reason we know is we have all these crack propagation lines going in different directions. And then over here, it's a big step. So whatever was going on here eventually merged with this crack. So those two are two independent cracks. And you can see on them where the crack was at a certain point in time. And that continues across to this side. So it's a real, I think you could see it in 3 dimensions that you have maybe 30 cracks here, at the, or maybe 10 cracks here at the beginning. Some will grow faster and eventually converge together to make only 2 big cracks with that step. And then eventually that step even disappeared to make it just one continuous crack. You have the same process going on the other side, and all you're left with, the overload zone, is what is a little bit more of a matte finish here. It's not shiny. That's the final fracture. Very little left. So we'll see in the second part today examples of how we make use of this to know what happened and prevent failures. Okay. Please load.
Your poor computer.
Yeah, I would change, but then I need to reset network, computer, printers, and all that stuff. It's not that old, but is this running? Yeah, so that's good.
Like computer projections. Or more if you're imagine like a Windows 8 tablet or software here when he's teaching us. If you would actually see that he's a cutesy version of it, like Demon Clown. He is working, so.
You would think things will become easier with all that improvement. It should be just showing the presentation, so now I have to dig it up again. Cancel. All right, let's see here. All right, I'm sorry guys. I'm glad I brought some example so we could get started. In terms of forming plastic, the injection molding is a very, very common technique. And the reason is the same way we talked about making aluminum casting being not expensive because of temperature. If you think of plastic, it's even cooler. So you can make all the molds out of metals. You have very simple cooling system with water or just a circulating fluid. And you can make parts at a very fast rate. So it's a little bit like a die caster here that we have, but instead we are feeding into typically pellets. So the polymer is made in this huge factory, and they don't make parts. They will make essentially the real compound to be used, and they make it in small pieces, looks a little bit like dog food. And then all you need to do when it comes to make the parts is you heat it enough so it's fused, and you inject it into the mold. You can make very complex geometries. One thing to keep in mind is how you deal with the ports. And the funny thing when you look for plastic forming, by far, injection molding is the most studied because of two reasons, right? So it's the least expensive, but it's also leads you to the most number of possible issues. This image didn't come out very well, but it's essentially a thread and nut that was used on a big exhaust system. It probably should not have been plastic, but somebody thought it was a great idea because it was corrosion resistant. So it was a composite, injection molded, and you can see this little tab. This tab had no reason to exist other than for the molding process. It essentially got damaged on this end here. Probably during service, there's no reason why they will cut that part out in the factory, and that's really where the crack started. So from analysis of this, we've looked into, the image is not really good. Next time I'll bring the part, next time I present this. But you can see that essentially the resin is flowing from this point. So this is not really what we call the mold line between injection point. This is at the injection point. And the only reason why you could initiate here is, first of all, you're in the bigger diameter, so as you torque it up, you get more stresses there, because that knot's going to grow in diameter, so you get more growth on the outside. But also, when the second you break that tap, all your molecular orientation and everything that we talked about skin last time, you lose it. So you lose the skin, and when you think about how it was injected and it was starting to flow this way, flow this way, flow this way. So right over here, if you can think that the macromolecular are actually oriented in this direction, and when you torque the knot, it's pulled in the other way. So if you put all that together, here you go, you had a crack. This one was, pretty consequential, so that's why I was able to do some detailed analysis and essentially finding that the shop itself didn't do anything wrong. It wasn't a question of temperature or control of the injection molding. It's just this idea that they were going to inject from an area here of high stresses, and at the very end, have such a protrusion that you can break it and essentially make you pre-crack. Because we clearly saw under the microscope that the transverse crack started from the end of the breaking crack of the knot. So I think it gives you a little bit of an emphasis that for long term, I mean, this knot essentially failed after 5 years. Nobody touched it, apparently anyway. And it essentially is a sort of a creep process that happened, so you don't see it right away, and it's associated with just very, very small changes on the surface. So it's a little unfortunate, like a lot of other parts, and they make a lot of efforts in the injection molding process to try to avoid all these mold lines, of course, but it's very difficult. Extrusion now, and I brought a section of pipe, doesn't have as many issues, so you make the equivalent of wrought product here. You don't need to go through deformation processing. Typically, you heat up your pellets the same way that you'll do in injection molding. It goes through the die, and there you go. You have a pipe, or you have any shape you want. You have a sheet. Pipes are very common. Now, one thing that I do want you to keep in mind is the practicality forces us to do an extrusion here. But the extrusion means that all our material is preferentially oriented in the direction of the pipe. Now, the hoop stress is actually higher in the other direction, transverse to it, and there's nothing to do about it. Unless that may be an idea for your project. If you want to make a pipe that's much better, then you want to have the molecular orientation around it, because your hoop stress is twice the longitudinal stress. So having said all that, when we qualify pipes, we do need to test them in the transverse direction because those are the properties that are relevant. So we can either take a sample and mount it in a very special way so the grip are like half a circle on each side, half a cylinder, and we pull on it. It's got a little bending. It's not perfect, but it's the best we can do. Or you pressurize it. And that's when we were talking about the 10,000 hour test. I'm sorry?
I just blow it up.
Yeah, so that's another question. So if you do that on a pipe like this that's able to take a service pressure of 200 psi.
Like, I don't think that's actually a good idea.
Well, no, it's done. It's done a lot. Yeah, for fittings, yes. But it will blow at 3,000 psi, so you need a very nice big enclosure. And it only gives you so much information because that's against the yield and the deformation as opposed to all this discrete behavior, the viscoelasticity and viscoplasticity that's controlling. Yeah, so the 10,000 hour test, you don't need a huge enclosure because then you're doing it at 400 psi and with water. So it's not a big deal then. Yes. Now, but the fittings for this is small, but if you look at big drainage fittings, they can be tested in a range of 2,000 to 3,000 psi. And then they'll fail in service at 200.
How long is 10,000 hours?
About 4 months. Yeah. And then, so you learn something after 4 months. It's not necessarily the answer you want. So there's a lot of iterations in that process. So when we were on the injection molding, I mentioned about the ports being a problem. Here we have the orientation, and there's also something else. We think of plastics as being, chemically resistant or non-corroding, but it turns out this is the most typical pipe used for light commercial, so not necessarily a big building, but new condominiums and office space are starting to use this plastic, even though it's high pressure. So 200 psi is about, we say the running water at MIT is probably 60, 70 right now. So we're looking about 3 times that much for sprinkler systems, and it is plastic. And I think we can all agree it's not just because it's more corrosion resistant. I mean, you can make cast iron pipe that will last at least 30 years and make the building owner happy. So it's cost. Putting these pieces together, you have essentially a solvent cement to put the different things together. If anybody put together a central vacuum system, you have all these little plastic fitting. You put a little bit of the adhesive. It melts a little bit the surface of the pipe and the fitting, and then you're done. These are all socket joints, and you move on. You don't have to worry about pressure testing or having a small leak. It's very uncommon. So it's very cost efficient, but turns out the past 15, 20 years when that system is used and there's a little bit of lubricant. When we talk about lubricant, it's just the cutting oil to make treads on pipes. Introduced into the system, that causes essentially cracking, small cracking of that plastic. It's been the biggest problem with the CPVC system because it's very hard to avoid it. So they had to work the past 10 years to keep improving the resin so it does become more resistant. So you can think of the oil as a little bit of a solvent for the polymer. So it does want to penetrate into it, and if you're under stress, it causes these stress cracks. So you see the stress cracks on the lower half. They almost go all the way through the thickness, and this is just a cut, a saw cut on the other side. You can pass it around. And I'll show you on the microscope right now what it looks like. I'm a little bit out of it. So this is the inside of the wall, and the outside is on top. You can see these small cracks. And in the context of what we looked at the beginning of the class, this is a crack arrest line. So at a certain point in time, we had a crack this big. We have our crack propagation line right here, because we had another initiation here. So on that fracture, what you'll see is a lot of individual initiations that are spaced maybe 3 millimeters away from each other, approximately. So what does that tell us? Tells us that the problem is not one inclusion, right? If we had one inclusion, we have one crack and it will just grow and cover the space. So initiating was very easy, and most of the time was spent in actually growing that crack through the wall. It's something that comes up over and over and over again in failure analysis. When I have one initiation site, yeah, there's probably something very special there. But when cracks are initiating everywhere, it's either there's too much stress, or in this case, that the environment is contributing to the initiation of the failure. So what do we do about it? Again, you can ask the plumber not to use any lubricant. There's nothing wrong with asking, or at the very least, make your material as resistant as you can to contaminants that you can anticipate in plumbing. So it's been a big adventure. The companies that sold all this system, of course, didn't know all the problems they were going to have. And then when you start having trouble, sometimes it takes a little bit of time to realize, well, okay, it happened to this person. Maybe they really put some strong chemicals in the pipe, and then you start having 10 calls and realize, oh, we have a problem. So now you start making changes, but it takes a lot of development. I mean, these tests at 10,000 hours to know if you started initiating cracks with one compound and then you do it with another compound, and what else can be in there, even from the water treatment. So I think, if nothing else, it'll point to you that a big change in material in an industry can sometimes work like perfectly. It only has benefits, but in this industry with the fire sprinkler, they had a lot of trouble. And now a lot of it turned out to be a problem for the insurance companies, because this is flood damage to a building. So to some extent, if the engineer, the mechanical engineer who designed the system just went with people have been using for a couple years, things been going well, they could not know. But you look at it 5 years down the road and say, well, this was not a product ready for service yet. It went, but they could have done more smaller scale testing to figure out that they were going to have a big problem. Blow molding, we talked about. This one, I don't have anything wrong with it, because you just make plastic bags with it, you make bottles, you make little enclosures. It's very similar to extrusion. So over here we have our polymer flowing, and one difference here, at the turn we also have the air coming in. It's one way to do it. You don't necessarily have to do it this way, but this way it's a very continuous process. So you can just have this run. The main advantage of all these processes is you start the machine, and your first few maybe 10 or 100 feet are not really top quality. It takes time, and you have waste at the beginning. But when you reach a constant condition, you're controlling very well your flow, your temperature, so you keep making it. You don't stop the machine anymore. So it's used in continuous form. It's used for these plastic bags, but you will also use it for bottles. It's a little bit more intermittent. If you're doing a bottle, it's a step-by-step operation. So you need all of this here to essentially be insulated. So when you stop the flow, your temperature profile doesn't change. But it is done. Perhaps the last very common technique is compression molding and resin transfer. Resin transfer is very useful with composites. So if you essentially use a mat or a reinforcement that is reducing the ability to inject the resin into it, it's a lot easier to lay your reinforcement and put a sufficient amount of resin and just really press into it. So that's done a fair amount. It's a more expensive process because in terms of speed, you have to lay everything down, then you close the mold, and you have to let it cool before you put the next one. And it's not a problem that we have with all the other processes that we looked at. Very much slower. Now, you can do other things, and somebody last class asked me about references, and for plastics, I've ended up using 3 or 4 different ones, so I'm not sure. And I think the reason is I didn't want to just cover injection molding, because there are a lot of really good books on injection molding, but if you want to be more general, it's very difficult. So I injection mold this, and this one is just a spring for my binding. It's the old generation from the 90s. So you got the spring here. Which end does it fit in? Not this one. Anyway, so the idea is there's a component here that's always loaded because there's a spring for the rotation capability. And a couple, maybe 5, maybe 8 years ago now, the whole thing came off. It was very cold weather, just getting off the chairlift. And, it got me thinking. And I found what the problem was just by looking at it. There was a tread there. So you can see that yellow zone? Mm-hmm. It's from the root of a tread because this zone is all tilted all the way to the corner. So this crack was there for a long period of time. Now, 20 years, really? So the truth is, and that's something that I do want you to keep in mind with all these plastic components, is they do get X-ray degradation and also oxidation in service. It's one of the biggest problems with polyethylene. So if I make a polyethylene component, what I need to do is I put what they call an antioxidant package. And it's a lot of these are proprietary, and there's some reasons for that. Somehow it's not considered mainstream engineering. It's kind of, if you want it to last for a long time, you do these things, and then the companies started to each have their own way of doing it, and it never got really standardized. It is tested, so if you buy a resin, you can essentially subject it to a temperature ramp, a few degrees per second, and you say, I want it not to start losing weight until 200 degrees C or whatever your criteria is. And that's how you know if the resin from vendor A is better than the resin from vendor B. Now, the reason I'm mentioning it is there's no way I could have abused this the first 5 years of its life. Nothing ever happened because it was fully intact at all the large molecular structure. When I start losing the antioxidant package, now I start breaking these big chains. So my molecular weight is going down. It's probably going down even more in the regions we have stresses. It becomes a little bit of a stress-induced, time and stress-induced degradation. And the way they describe it a lot is it's like wine. Wine gets better, gets better, gets better, and then eventually it turns vinegar. So if you run out of antioxidant, it's very dramatic. From one day to the other, yes?
Is this an additive that you put in the polymer?
Yes.
So it's not a coating?
It's added to it. It's a very small, and I know a few about, I had to do research with it, but I can't even, what I tell you is they're not very long molecules, and they'll travel and essentially attach to any broken chain. And that's how you prevent further degradation. Maybe the best example of that is these flexible pipes. In terms of So nothing happens unless you reach that critical point in time, and then it is a function of how much package you've put in the first place. So it's just the same way that you'll specify, I think I mentioned at the beginning, you'll specify a certain welding process. Well, if you don't say exactly what you want for your long-term chemical resistance of polyethylene, you have a problem. The PVC, so the orange one over there, doesn't need an antioxidant package. It needs other additive to prevent stress cracking, but it's not susceptible to this oxidation in the environment. So before I go to this polymer, I want to bring in this one. Just another example, completely. So what I was trying to do today is give you different case of analyzing the failure that gives completely different outcome in terms of what to do. This one relates to this antioxidant package. So it's flexible plumbing. When we mean flexible, so there's a limit, but you can essentially put that into your home without having joints when you go from the floor to the back wall all the way to the appliances. The way we put these together, this is the most common plumbing system right now, is you do have some fittings. You need to make connections. So the polyethylene is so flexible that we have an expansion tool. So we just grow the inside diameter, insert the fitting, and the viscoelasticity contract everything back in place. And there you go. You got a plumbing joint. This is one that was taken apart here to make sure it's strong. When you expand, you also put that little ring that reinforces it. So you start like this, you expand with the ring on, put the little plug here, and here's your joint. That's it. It takes about 10 seconds to do. And there's no real way to mess it up. When we talk about like welding and soldering and putting the flux and all the other things, this one, as long as you put the pieces all the way in, it will be a proper installation. You do have to cut the pipe straight, but they have tools for that. Yes?
So is the problem of oxidation unique to polyethylene, or are there other plastics that as engineers should we be worried about, this corrosion?
You have to worry about it in polypropylene as well. I believe nylon degrades too, but not necessarily at a rate that absolutely requires an antioxidant package. It's good. There's nothing wrong with putting it. And the main thing that I'll point to you to is depending on whether you need it or not is a function of your service temperature. So one of the problems that I'm going to introduce here is they were using polyethylene. Now, if you recall from last lecture, we talked about polyethylene. I say, we have all this creep problem with pipes. It's a big issue. Well, this one is cross-linked after it's completely formed. So they put essentially activation a particle for cross-linking into the polypropylene, polyethylene and polypropylene. You essentially extrude it into a shape, and then by exposure to moisture, it becomes a little bit of a thermoset. Now, it gets some cross-linking between the molecule, and that's why it's got a good resistance under pressure after that. So it could be used for high pressure. It's flexible. It's got a lot of advantages. One problem, you can kink it, right? I got plenty of these. So one problem that a practical plumber doesn't like this, right? They don't want to be like, I kinked it. Now I got to cut another one. I need to get some more fittings and all that. So there was a technology put together where instead of just being polyethylene, you added a little layer of aluminum in the mid-wall. And these are still out there. They're pretty useful. So you have a little inner layer of polyethylene. That makes sure that you don't contaminate your water. And essentially you're using the same environment than the other PEX pipes that are very common. Then you put a little layer of aluminum. Now the layer of aluminum here had a very specific purpose, but from the way it was designed, the idea was to prevent oxygen from inserting the system. Their intent, the people who developed this, was I will use this when I have radiant heat. So in a home, you put it under the floor everywhere, and then when you turn it on, it goes to the hot water heater and essentially heats the floor constantly. The only way that a good hot water heater works is if it's a closed loop system and there's no oxygen coming back. Otherwise, you corrode it very quickly. So there was this purpose of the aluminum, but then the plumber said, hey, this pipe, I like it much better. First of all, if you have the aluminum core, if you bend it, it stays bent because the aluminum keeps the shape. So there's been this growth in the use of the product for potable water. The problem with potable water is now they had essentially oxygenated water going through it. And instead of having the resin last for the original intent 20 years, it lasted a couple years and then started making these big blisters everywhere and leaks. The problem always with plumbing is it's inside the wall, so nobody is happy because then you have to tear down a lot of walls to repair. Yes?
So what's the relative cost between this more complex tubing versus the simple one?
Oh.
Why not just get corner fittings and use the barbers?
It's very limited. I mean, maybe you're looking at a 20% margin, and the tubing itself is such a low cost as opposed to the installation. The only problem was the people that were making this didn't realize that it was also going to be used in high oxygenated water environment. So they didn't change their antioxidant package. They used the cheaper antioxidant package. There's a cost associated with that antioxidant package, but by the time they fix it, it's still used. But this is exactly like the CPVC system. It's down the road that they were able to avoid the problem. It was a little bit of a bigger problem with hot water. You get a little bit more oxidation, but it was happening in all the cases. So kind of another learned by mistake. You think, oh, I'm going to design my factor of safety of 5 or 6, and then something else that's completely different happens. And from where we start today, this is where the history of service really comes in. If you sit around and try to think, well, you know, what's going, maybe, but you need to think a lot. You know, the normal engineer, or especially the mechanical design engineer, like, oh, well, you know, we've used PEX for a long time. This is PEX again, and it has aluminum. So it was actually advertised like, oh, you got an extra barrier because if there's any water that tries to penetrate, it gets to the aluminum. Now it turns out that when you start having so much oxidation, the acidity inside the polymer goes way down. It's like you get to pH 3, and at that point, the aluminum corrodes very, very quickly. So it wasn't a barrier to the water. It just got poked into it. So now to tie back into our processing, I do want to just make you imagine a little bit. You think that this is hard to do, but a little bit in the context of what we talked about, if you have an extruder and you feed plastic in the center, you have the aluminum sheet that you bring in, you fold it, and then you put a seam weld, and then you have some extra resin to put on top. This is a one-time operation, all done at once. It's not perfect. There's a little bit of wall thickness fluctuation depending on your level of control, but there is essentially a very productive way to making these pipes, and they still make them, although the original manufacturer, I think, just went out of business. Somebody else had to take over. Okay, one last example that's completely different, and we're going back to metals for it. It's a piston head for a big combustion engine. It broke here, so you can see that it's missing into just an inline Volvo engine. So what happened is this is mechanically attached. The head here is mechanically attached to this rod, the push rod, with using a certain form of a compression fitting. And we had the transverse crack right there. So I think so. It's a rod product, so maybe it's just that there was too much load applied to this head, piston head, because it was essentially, if you start touching the head of the cylinder in one area, you can, when you close, you can have some bending loads. That's one option. Maybe there was an inclusion from manufacturing, and maybe we don't know. So somebody sends it along. We look at it. This is what it looks like at first. The only thing I can tell you from here is I do see the crack arrest line up above there. So I'm already able to tell you there wasn't much load applied to this. I'll circulate it so you see the big arrest line over here. And there are two initiation sites. We'll cover that with the micrographs. That's just a few rotated images showing it's not really a straight crack. All right, so we're looking at the top here. This is the final fracture, and you can see it on the sample. We had one crack here, and we can see the arrest line. And it's not really clear on this image, but I identify another crack here, and we'll see in the detail how relevant that is. So started small. You know, I'm looking at it here. It's out of focus in the initiation area. So that means there's something missing, right? Was it a notch? What exactly was it? But there's just a big piece, just about 50 micrometers, 100 micrometers, that's missing on the surface. Somehow, though, this image, well, I'm not the one who took it, but when the engineer came with it, I was like, well, I can't really see what happened. Then we look at another one that I thought was a lot more interesting, because we clearly see the end of that void, and from there we start seeing all these small crack propagation lines, a lot of them. So what this specific image allowed me to say conclusively is this hole preceded the formation of a crack. It may look obvious, but it turns out the hole is just a corrosion pit. So it could have gone the other way around, right? You break the engine, and then there's, you know, circulating, cooling fluid coming through it, and then you pit the shafts. But in this case, it's very clear that this was already there, and then you started a crack. So the most likely thing that happened is the engine wasn't used very much or well lubricated, or there was one last maintenance that was done before, and then it started corroding, and it corroded and then failed. Now, are you going to blame the material? No. You know, so you're going down to essentially maintenance as the problem here. So that was significant, yet not super sophisticated. So that's one thing I think you can see. We do learn from experience, right? But sometimes it may take years before you actually get an answer for something. So if people have been using a certain type of process or material for something, it takes a lot of effort to make a transfer, because there's so many things that they, oh yeah, that's fine. You know, for example, you know, medical device, say we're using stainless steel, we have a special joining process. I can make something better, yeah? Okay, is it going to work in cold temperature? Is it going to work when they clean it with these strong chemicals? And what if the surgeon decides to bend it? Is that going to still work? So every time you make a change, I think is your opportunity to go back to exactly what is needed. So I would say for engineering, if we never had failures, I don't think we'll be at all anyway good like we are, because it's not that we couldn't imagine it, it's that we can exactly adjust to it. So my bindings, 15 years, they knew that. That was just planned for, right? Because they you know, after 10 years, you're supposed to change it anyway. They changed the design of it. So this one was not an error in terms of the product. It's me abusing it, trying to use it too long. But all the pipes that we talked about, that's a really good example why some people resist using plastic right now. They still want to use copper pipe, even though the price of copper goes up, because they do remember all these issues that people had. So, for me, with my startup company, I'm thinking in this way, that we want to be successful the first time, because otherwise you get a bad impression. Like PVC fitting got a bad impression in the any plastic at this point. You have to really justify it in plumbing. People don't like using it. So, all right, thank you guys.
Thank you.
So tomorrow